So Dr. Jayfus Doswell is a high-tech entrepreneur and visionary futurist with a mission of improving human performance of populations, underserved and disadvantaged. Dr. Doswell earned a Bachelor of Arts from Oberlin College with degrees in cognitive neuropsychology and computer science, a master's degree in systems and computer science from Harvard University, and a Ph.D. degree in IT from George Mason University. Doswell's dissertation, defended in 2005, created the world's first culturally competent, empathetic, and ethical AI virtual instructor software architecture to deliver personalized instruction to underserved populations in mixed reality environments. Dr. Doswell is the founder, president, and CEO of Juxtopia LLC, a privately held for-profit biomedical and IT company with a mission for improving human performance. Prior to starting Juxtopia, Dr. Doswell leads several commercial engineering teams at Fortune 500 companies, ranging from Lockheed Martin and SAIC to KPMG as their senior software engineer. In his 20s, Dr. Doswell was Lockheed Martin's youngest senior software engineers in the United States. Dr. Doswell contributed to early biomedical and nanotechnology informatics algorithms while working at the National Cancer Institute to help create better cancer treatment. Additionally, Dr. Doswell invented and wrote federal government SBIR or STTR proposals to secure research and development funding for the development of Juxtopia's innovative wearable technology products for improving human health and learning. So thank you, Dr. Doswell, for finding time for our workshop.
Well, thank you, everyone. I'll put on my video. Thank you, everyone, for allowing me to present to you today. Today's talk will focus on artificial intelligent augmented reality police e-trainer for culturally competent de-escalation and non-lethal force police training to eradicate police violence against Black males. Please forward slides. You all remember this image that was a horrific time in our United States history, and that prompted changes in United States police training. Next slide, please. A little bit of background. Thank you, Dr. Gupta, for that wonderful introduction. I won't reiterate most of this, but in addition, after my dissertation in artificial intelligent embodied conversational agents that teach human beings in mixed reality environments, I became the director of the Virtual Instructor Pilot Research Group that falls under my nonprofit organization to advance artificial intelligent educators to pedagogically and andragogically tailor instruction to human beings in augmented reality, virtual reality, and holographic environments. Also, I helped create the Health Informatics and Information Technology section of the largest public health association in the United States called APHA. Next slide, please. Baltimore police problems. Most innovations, follow a painful problem. Police problems in the United States have become in a pandemic for a long period of time. It was an epidemic. There are poor interactions with community that increase racial disparities. There's a disproportionate targeting of residents of minority ethnicities. And then police are oftentimes not trained appropriately to de-escalate when encountering citizens that are maybe suffering from mental crisis or having a bad day, and then stereotypes start to percolate, and then show in the behavioral form that's adversarial in many respects. There's also a depreciation of nonviolent alternatives aimed at peaceful resolutions that police can learn. And that's the focus of this presentation today. Next slide, please. In Baltimore, Maryland, there are consent decree challenges because of the Freddie Gray case and the historic violence of police. That can change, but that's been appropriately recognized. So now police are taking more accountability based on what you see here on slides. Next slide, please. So what can be done to improve police training? Some synthetic training simulations based on other ancillary type of studies, such as military, healthcare, in different civilian areas. Training simulations have proven to be very effective to achieve a learning outcome that's measurable and that's consistent. So also training simulations can help to control and measure variables, provide supplemental training to target and to improve the competency of training deficits, facilitate practice repetition in stressful situations, and in the context of police training, through repetitive cognitive-based therapy or training, minimize potential PTSD by exposing and preparing police to work in austere and extreme environments, similar to military. And I'll get into some of these case studies later on in our presentation. Next slide, please. So this is a familiar photo of how virtual reality is used in police training. Here, this is considered a fish tank virtual reality apparatus. There's three types. There's desktop VR, fish tank VR, and fully immersive virtual reality. We're in the frequent user interface and modality of fish tank virtual reality. That's when you have a head-mounted display like Oculus Rift. You can't see in front of you. Your whole senses, your visual acuity is really immersed in a 3D simulated environment. But if you try to run, in any direction, then you may somebody may hurt themselves. So that's why in this case, the police is shown tethered to a fixed area, geographical area, focusing on shooting techniques with fake firearms. Next slide, please. Conversely, this is a view of an augmented reality police training environment that my artist in Juxtopia devised, where on the right-hand side, you see a pictorial mnemonic based on cognitive science on multimodal methods of actually presenting information to human beings, the scanning environment, ability to identify using computer vision techniques, human beings in an environment, and also other objects that are non-human, and then to accurately and reliably detect both types of entities within an optical see-through display. Next slide, please. So I'm gonna go through some case studies on the context-aware mobile mixed reality assistive platform that served as the basis for Camrad Police, and from which reusable software and hardware systems were created based on a product line architecture, which I was trained by Dr. Goma at George Mason University. And when he was on my Ph.D. committee, he wrote the books on product line architecture. Next slide, please. So augmented reality, unlike virtual reality, is supplements or presents digital artifacts that are superimposed on real-world environments and objects. So the benefit of augmented reality is that it provides a live, direct or indirect view of the physical real-world environment, where the elements are augmented or superimposed as artifacts on the real-world environment, and that's the visual elements, but also other types of artifacts that augment human perception, like sound and tactile as well. There are two types of augmented reality. There's mobile augmented reality and there's wearable augmented reality. Mobile augmented reality is viewed typically from a phone or a tablet, where the video, the camera, becomes the eyes, your eyes, and computer, software algorithms identify those objects in the real world and then put 3D or 2D or text type of media superimposed over those real world objects projected and seen through the camera view. Conversely, wearable augmented reality is an optical see-through display where the physics of optics, the reflection and refraction of light, where there is like old school beam splitter, like Google Glass, where that would present information right there in front of you at a certain field of view and a certain focal distance. Two different modalities, two different technical challenges. Both have their benefits and cons, pros and cons. Next slide, please. All right, in 2010, Juxtopia engaged in research with Morehouse School of Medicine, training first and second year medical school students on how to perform a needle decompression procedure. This procedure is a response to a tension pneumothorax, the second leading cause of battlefield death, for which a four-step procedure is administered typically by a combat medic or field medic in times of war. Four-step procedure is, as you see on the left-hand side in that viewpoint, the hand represents an icon. That's step one. Step two is another icon, and step three and step four, respectively. Those are all icons that are intended to trigger the activity of that step. So, for example, step one is apply antimicrobial scrub or clean site. Step two is to stick a 14 gauge needle in the second and third intercostal space. Step three is to catheter, and step four is to listen to the breathing sounds, because at this point, if the medic has done the job correctly, then the pleural fluid in the lungs will be released, and then the casualty is now saved. On the right-hand side, this viewpoint, that's an actual view from a cell phone held up to our first version of augmented reality goggles. You can see the display in 2010, even though it's monochromatic, polychromatic, multiple colors, it's kind of attenuated because the cell phone's camera is, diluting or attenuating the image. But in this case, you can actually see that, these are instructions and graphics and icons for how to perform this procedure on a mannequin. Next slide, please. When we did the study, we looked at quantifiably how this type of modality, we were calling this pedagogical agents or andragogical agents, even though the core foundation was always artificial intelligence. But only until recently, computer scientists would use artificial intelligence without negative feedback from their comrades. So today's a new day. So in this case, we looked at the 4 steps and we evaluated step completion and step accuracy, step time as dependent variables to determine how this modality can improve the performance of first and second year medical school students performing the needle decompression steps on real world cadavers at Morehouse School of Medicine. Next slide, please. Another case study that serves as the foundation for Cat and Rat Police is one that we received. We secured a National Institutes of Health, SBIR, worked with Maryland Fire Rescue Institute to train EMTs and paramedics on how to perform a variety of procedures, medical clinical procedures, applying a tourniquet, pressure bandage, administer an IV, and I think we did needle decompression as well. Next slide, please. That's one of the EMTs wearing an augmented reality head-mounted display. And then some of the images that you saw before we presented through this display. This one had a clicker so that we would minimize the errors that could happen during speech recognition or speech navigation of an augmented reality display. In this case, speech recognition and speech synthesis are a type of artificial intelligence, but to make sure that we didn't have any confounding variables that would distract from the data results of improving the EMT's performance through an augmented reality, by looking at the steps of a task in augmented reality. We made sure we could control that and control that variable so that would be a consistent modality for the user. Next slide, please. This is another view at the Maryland Fire Rescue Institute, where the medic, in this case the EMT, is looking through the augmented reality goggles, following the steps of an artificial intelligence instructor, and then consequently being evaluated by performing a tourniquet on an arm. And that's not the person's real arm. That's a millage, fake arm, but it helped to increase a sense of realism in the synthetic augmented reality training environment. Next slide, please. Another study we did was a $2.1 million contract from the Pentagon. It was a rapid innovation fund, required a SBIR or STTR phase 2 to go in, or technical readiness level 6. We completed that successfully in 2 years with institutional review board at DOD, Johns Hopkins University, Coppin State University, and Juxtopia, a multi-part IRB. And in this case, you see a medic wearing a HoloLens, first HoloLens, performing a cricothyrotomy. That's a very complicated procedure for which a slit is made in the airway. A breathing tube is put in the airway in order to sustain the casualty for medevac pickup and to go into the rear. The young lady in the back with next to the other mannequin is the control group. So we did experimental group, control group, side by side per task, a task being a cricothyrotomy, needle decompression, IV tourniquet pressure bandage, and then measuring dependent variables of time, accuracy, and completeness among each of those steps, and recording that quantifiably, and then publishing the results. Next slide, please. This is another view, and I have video that I can share with you, Dr. Gupta, afterwards. You know, but this is another view. If you running through this, you'd actually see the step-by-step instruction, voice activation, the speech navigation, speech synthesis with speech response, and then even fiducial market overlay of a mannequin, like blood coming out of the mannequin. That's what, based on our focus group and surveys, the medic instructors desired to make a more realistic training environment for the medics who all train at Fort Sam Houston in the United States Army at 68 Whiskeys. Next slide, please. We also did a comparative study with nurses who perform similar tasks as medics, but nurses are in a higher training echelon than your medics. We're pretty much at EMT basic if we were doing the parallel between a 68 Whiskey, U.S. Army 68 Whiskey, which is a combat medic, and a civilian EMT. They're pretty much equivalent. A nurse is trained at a higher level, but each type of skill, job category is trained in intravenous, administering an IV. So this is where you see right here, initiating a direct line and looking at experimental group and control group. Again, being very consistent on the dependent variables, measuring quantifiably accuracy, time, and completeness. And what we found here is that the time in the experimental group increased, in the control group it decreased. So, different from what we initially expected, and unintuitively, the experimental group time increased, and this was consistent between the nurses and the medics, because they were spending more time looking at the instructions, following the instructions from the artificial intelligence instructor, which means that in the Bloom's taxonomy world of effective conceptual and psychomotor learning, the effective of paying attention, being motivated to attend to this skill for which someone wants to learn, in this case, the learning was taking place. We did not do a time lapse, which is typical for experimental studies like this, for evaluating if the information is getting into the hippocampus region of the brain, and you have present the intervention or the training. You take some time that elapses, and then check recall if someone has retained that information. But in this case, we did evaluate the attention of that information throughout the steps of a specific task. Next slide, please. This is based on our experimental results. So we came up with a solidified and uniform user interface for delivering steps in an augmented reality display. On the right-hand side, you see a pictorial mnemonic. Now we call that a multimodal mnemonic because not only can we present iconic representation of each step in a task, but in that middle area, we can present video, animation, and graphical pictures and photos. On the left-hand side, that's where your checkboxes are for checklists that are very important cognitively to trigger memory of a human being performing a task. And then, of course, the system icons and descriptions right there in the same view. This switches between this view assistant mode when someone's practicing the task in a real-world environment beyond training, and also training mode, where if it's an adult, andragogical algorithms based like scaffolding or other andragogical type of methods that are codified, or pedagogy if it's for children, such as jigsaw, scaffolding, and facilitating constructivism environments. Next slide, please. Now we get into CANRAD police. So based on the years of our doing this type of research that really started in 2005, the National Science Foundation STTR grant to create an industry agnostic product line architecture of delivering target systems that are artificial intelligence enabled augmented reality. We did secure a grant from NIH to tailor our platform to training police to de-escalate. Next slide, please. We had young engineers working on our project. This is a young engineer, a computer science major from Bowie State University, who's writing Python code to detect various objects in an environment. Many times, historically, police have mistaken cell phones for a weapon or an umbrella for a weapon. This young man's focus was on training a computer vision algorithm to recognize various objects in well-lit or not well-lit environments to create a cognitive assist for police so that they could de-escalate effectively and potentially mitigate mortality against underserved and disadvantaged populations. Next slide, please. This is another image, even though Shutterstock. It's to show that a pistol can be detected from his algorithm and then presented right here in display. Next slide, please. This young lady focused on gesture recognition. She used another type of Python binding with OpenCV, Open Computer Vision, to recognize hand gestures, so that in certain noisy environments, we know that speech recognition has many false positives and false negatives. So there has to be like a contingency plan to navigate the user interface or control the augmented reality's microservices to deliver the information. So she came up with a set of gestures to navigate the the augmented reality user interface for the police trainee. Next slide, please. Next slide. And these another one. So this one was to remove the interface. So that's the augmented reality. Now we're going to get into another wearable to support the augmented reality. Well, as in computer science, computer scientists know that computer vision and hidden Markov models and convolutional neural networks, even though trained, is computationally expensive and very computationally expensive to run on a microcontroller on an augmented reality head-mounted display that is ergonomically comfortable for a human being. Granularly, there's another type of science and computer science called human activity recognition. That's where each step in a task can be evaluated based on data that's generated from multiple sensors, like an inertial measurement unit and electromyograph sensor. So in this case, I invented a Juxtopia Imhotep band. It's an armlet that encapsulates two sensors, an IMU and EMG, and then generates that data and does the pre-processing of that data on client, and then subsequently does another set of pre-processing on the IMU Kalman filter, on the EMG Butterworth pre-processing, so that the segmentation and the feature extraction and the classification can then subsequently be done on the server side. Next slide, please. So this is one of my engineers wearing the G-band, and on the right-hand side, that's just the data, a snapshot of the data that's being generated that subsequently becomes a data set, and then it gets interpreted by our model, which is the police trainer model. So Juxtopia police instructor. Next slide, please. And this is our newer version based on the research results. We did a controlled study with police, and we also did some controlled study with nurses. And we came up with a way of now displaying configuration data, displaying the battery life of the device, and product development. Where it's like art, you learn as you go sometimes from studies and what the user wants. Sometimes the end user doesn't know what he or she wants or they want until it is used in a real world environment. And this great feedback that we receive from our cohort of subjects in our IRB approved study, then we're able to update and modify the G-band device. So here you can see, here you can see on the left-hand side, that's a micro display, an OLED display on the pod. That's running a microcontroller that's Arduino based. It has a micro SD to collect the data on client. It's running the programming language of Arduino, which is a flavor of C and C++. Once it gets to the server, we're running a 3-tier architecture, Java Spring enabled with the algorithm on the middle tier. And then we have flat files or ASCII files that are storing the data. And then we're running Deep Learning for J, which is an API for deep learning algorithms, running a long short-term memory neural network bidirectional LSTM on the time series data to classify it into our model. On the in the middle, that's Brandon. Brandon's one of my lead engineers, hardware engineers, and he put a simple button on the band to power on, and then on the right-hand side, he's expanded the actual pod with more comfortable and ergonomically more ergonomic straps with I guess covers over the wires, because before the wires would come off, and we learned from that experience as well. So even though this is prototype, this is a great prototype for our data collection. And then how it's used in police is that now we can track when the police is pulling for a gun or taser, and then depending on the EMG's data and how we train it, we can actually measure how that police what firearm or what type of tactile response the police officers making, and generate that into a performance report, and then present this to trainers to see really if that police officer is ready for policing and working as a police officer. So the augmented reality, then in combination of this armlet wearable, presents a more comprehensive type of training modality for the cognitive de-escalation training. With wearing the augmented reality goggles, the police will go into 4 different scenarios. And so we're preparing for our IRB study right now in August. Well, the police officer will go to a would do a traffic stop, which is the most dangerous type of activities for a police officer, and then simulate going through the motions and talking, where we have like African American vernacular English as a sentiment analysis and a transformer algorithm for natural language processing. So the natural language processor that's activated by the Juxtopia police instructor is interpreting in real time the utterances coming from that police officer and how he or she or they are speaking to a suspect. The computer vision then is activating, object recognition to look in the police environment, to help that police make better decisions. No, that's not a gun. That's a cell phone. Relax, have some tranquility, present that right on the screen so the officer is reminded and can introspect on what to do next. And then each action, the hand gestures, the nonverbal cues, as well as what firearms is that officer grabbing, that provides a nonverbal indication of aggression, non-aggression, and also we've had some of our engineers do face recognition and expression recognition to evaluate the face and expression of the suspect, to help the Juxtopia police instructor assist that officer make the best decision and help to de-escalate the situation. Next slide, please. That concludes my presentation, and I'm open for questions.
Yeah. Thank you, Dr. Doswell, for a wonderful presentation. And I have one question from one of your project, and then we will go with the audience. You said you have basically worked with the augmented reality and the virtual reality use cases that you have shown us. So are those devices are being developed by your company, or you have used some of the existing, like the Google Glasses or the other devices from the other manufacturers? Yeah.
Both. So the National Science Foundation in 2005 funded us to develop our own augmented reality glasses. At that time, there wasn't a such thing as a Google Glass or Microsoft HoloLens. Apple Vision Pro is not really augmented reality, not to augmented reality experts. It's a pass-through. But at any rate, we develop our own head-mounted display, and we use a different type of methodology. So it's more of a modular type of system instead of a fully integrated system for everybody. So we can custom design our augmented reality devices for a target audience. We also used commercial off-the-shelf augmented reality head-mounted displays, and then test our software to evaluate our software, and of course to make the software decoupled from the actual hardware, just in case our customers have a desire for the head-mounted display that's AR that they would like to use.
Okay. So in one of the use case in the figure, as you were showing for the needle decompression, in that one, like you wearing the glasses, the person who is inserting the needle, that will become like a virtual needle or something, right? Like that, but it's not actual, right?
Oh no. So in augmented reality, you're seeing the actual needle go into the mannequin or into the person. But instead of actually getting a virtual needle, like what you would do in virtual reality, then you could see a landmark of where to stick that needle based on someone's anatomy, so that there's an anatomically correct superimposed circle where you can actually say, okay, well, shows the person this is where you should stick that needle. So we've done a lot of work with combat medics. Medics are going out into the field and being fired upon. So they take fires called care under fire, and then that medic has to perform accurately in that austere environment is very difficult. So to have any type of cognitive assist when returning fire and you can see a circle, stick that 14 gauge needle, that actually can help save that soldier's life.
Okay, that's wonderful and really interesting work, Dr. Doswell. Is there any question from the audience? You can unmute yourself or put it on chat for Dr. Doswell. Okay, so it's really a pleasure, Dr. Doswell, for seeing your work, and we will look forward for collaborating on some of your work, like we were already discussing on some of it. So
Yes.
definitely it will be an interesting application in the healthcare domain for some of your work that you have shown to us. Thank you very much, Dr. Doswell, and
Thank you.
feel free to attend the workshop. We will have it until, I think you will be in the panel, so that will start at 3.
Yes.
Yeah. Mhm.
All right. Well, thank you so much.
Thank you very much. Yeah.